Hello and welcome to this second video on the geometric applications of derivatives. Okay, we've only got one thing to do this lesson, and that is to explain the methods to test critical points, because it's crucial to understand the two different methods and why you would use each different one of them. Okay, so the two different methods are, I'm just going to start with this, and we're going to zoom in a bit because we've got a lot of working out to do. So we do have two different methods to do this, and our two different methods are, the first one is going to be a table of values, right? Table of values. And our second one is going to be using the second derivative. So we did speak a little bit about the second derivative in the last chapter, and we're going to actually be applying the second derivative now for a purpose. Okay, so the function that we're going to practice sketching on today is going to be y is equal to x to the 3 minus 3x. Okay, like in the last chapter, what we're going to do to first of all figure out where the turning points are and their corresponding coordinates on the curve is going to be to derive. So first step is deriving. Y dash is equal to 3x squared minus 3. Okay, so taking the power down the front and deriving that just to its constant. Okay, now that we've done that, we need to solve for when that equals 0, because we want to figure out when the derivative is equal to 0, because that will tell us the turning points. Okay, so we get 3x squared minus 3 is equal to 0. We can do two things here. We can either divide by 3 on both sides, and we get x squared minus 1 is equal to 0, and do a factorization by difference of two squares. X plus 1 is equal to 0, so x equals plus or minus 2. Plus or minus 1, or from this point here, we could add 3 to both sides and divide by 3. So we would get x squared is equal to 1, x equals plus or minus 1. Right? Both methods work. So the corresponding x coordinates on our function are going to be plus or minus 1. How do we find the y coordinates that link with each of those? If we put f of 1, we're going to get the coordinate 1 minus 3 times 1. Or 1 to the 3 minus 3 times 1, which is going to give us minus 2. If we put in the coordinate 1, we're going to get 1 minus, minus 1 minus 3 times by minus 1. All right, so if we put in minus 1 into that function value, we're going to get minus 1, and that's going to give us 2 as our number, because those two will become positive, and then we will get 1 plus 3, which will give us a positive value of 2. Okay, so we have our two coordinates here. So we have the coordinates 1 and minus 2, and then we have also the coordinates minus 1 and positive 2. Positive 2. Those are our two coordinates. So the first method I'm going to show for how to tell whether these two turning points are going to be positive or maximum or minimum turning points is going to be using the second derivative. This is usually my preferred method because it doesn't include as much messing around and you don't have to substitute as many numbers in. It can also be useful for finding points of inflection, which we will go over next lesson. Right? So all we do for the second derivative is literally just do what it sounds like. We derive again. So from this here, we're going to derive once more. We're going to get y double dash is equal to, deriving that, we're going to get 6x minus 0. Right? Or plus or minus 0, it doesn't matter, because the 3 will derive to 0. Rightio. Now, what we do is we get these 2 points over here. I'm actually going to just move over to here. And what we do is we substitute each of the x values into this second derivative. So when we substitute minus 1 in, so f double dash of minus 1, we're going to get minus 6. Okay, the way we tell whether this is a maximum or minimum from this is super easy. What I like to say is if it's negative, right, it's negative, it looks like a frowny face, right? Frowny face. That's what a frowny face looks like with those eyes there. Now, if it looks like a frowny face, what type of turning point is this going to be? Well, it goes up to a high point and then drops down low. So if it's negative, it's a frowny face, and that means it is a minimum turning point. Oh, sorry, maximum turning point. Maximum turning point. Goes up to a maximum point and then down, right? So f of minus 1, when we subbed minus 1 into there, that's going to give us a maximum. Maximum, and when we sub f double dash 1 into there, we're going to get positive 6, which is going to be a smiley face, arrows up, right? Smiley face, arrows up, and that's going to give us a minimum turning point. Okay, so these are our 2 points here, and I'm just going to sketch what our curve will look like over here using this information. Right, so sketching across there, we have the point 1 and -2, and then we've got the point -1 and +2. Right, when I like to sketch this, what I do is I draw a little curve on it just to remind myself which way it's going. So on the one that's 1 - 2, it's a minimum turning point, so I just do that before I actually join the dots. And on this one here, I'm going to do that. I'm also going to label my points, -1, 2, and 1, -2. Right, so those are the labeled points. Now, if we want to figure out where it passes through the x-axis, what we should do is we should let y equals 0. If we let y equal 0, we're going to get x out 0 is equal to x to the 3 minus 3x, and we're going to get 0 is equal to x outside of x minus 3, x squared minus 3. So we're going to get the point x is equal to 0, or x is equal to plus or minus √3. We don't actually technically need that. It's just so that we can put more information on our diagram. Traditionally, they don't usually ask for roots. They may ask for the y-intercept, right? So where it cuts the y-axis. If we just want to find the y-intercept, all we need to do is let x equal 0, and then we would have got the point y is equal to 0, right? So what it's going to do, it's going to pass through here. And we now know what these two roots are here as well. This is going to be plus √3, and this is going to be minus √3. Okay, so that's how you do the maximum and minimum turning points, how to establish which one they are using the second derivative. What we're going to do now is have a look at doing it via the table of values, because table of values is really good to know, especially for some of the harder questions, right? Harder questions can be very difficult to find the second derivative for. So in that case, you would want to use a table of values. What the table of values is, I'm just going to copy these here, and I'm going to move it down to here, right? All the table of values actually does is it just helps us establish the maximum or minimum turning point. There's nothing different to find the turning points themselves. It's just whether to establish it's a maximum or minimum. Okay, what we're going to need, we are going to need a couple things. We will need the function eventually if we wanted to plot it properly, but all we need to do our table of values is going to be this first derivative. Y dash is equal to 3x squared minus 3. Right, first derivative is all we need. Okay, what we do is we have a look at our point here. So our x coordinate is going to be 1. So we draw up a table like this. So on the top is going to be our x values, on the bottom is going to be our f of x values, f dash x values. So at the point 1, we know there's going to be a gradient of 0. That's how we found this point in the first place. What I'm going to do now is I'm going to do one that's slightly either side of it, right? So it's important that you put it in chronological order, so increasing order. So the one that's smallest to it is to the left, like it would appear on the number line. The one that's larger than it is going to be on the right, like it would appear on a number line. Okay, so if we put a half or 0.5 into our first derivative, what we're going to get is we're going to get y dash is equal to 3 times by 1 over 2 all squared minus 3, which is going to give us 3 over 4 minus 3, which is equal to minus 9 on 4. Right? You could also put that into your calculator, or you could do it as a decimal. Right? So what's really important is I don't actually really care what that number is. All that I care is that it's a negative number. Right? It's a negative number. I care about its sign, not about the actual value. Right? You still need to show the working out to show that you established what the value was, but the value itself isn't that important. Okay, when we put y dash, when we substitute 2 into our first derivative, what we're going to get is we will get 3 times by 2 squared minus 3, which is going to give us 12 minus 3, which is going to give us 9. Right? And 9's good because it is a positive number. So 9's going to be positive, so what we do is we put positive here. Now, what this is actually saying is that if we're thinking about this from a number line perspective, right, going along a number line, at a half, at the value x equals half, the gradient is negative. That means it's decreasing, right? So would you agree that a decreasing function, if we were to straighten it out, would look something like that? Right? So that's what the decreasing function looks like. What does a function look like when it's at 0? It goes straight across, right? And what does it look like when it's increasing? It goes up. So we've got negative, 0, positive. And if we have a look at that, it forms a upwards curve, which would make this a minimum turning point. So does that correspond to the one we got before? When we checked it in the last one, we got a minimum turning point at the point 1 minus 2, right? So this is a minimum turning point. We're also going to do the same for the second point. We're going to also draw up another table of values there, right? So drawing up another table of values is going to be very similar for this. We're going to get x, f dash x, and then we're going to have minus 2, and then we're going to get minus 1 and minus 0.5. Okay, you don't actually need to put in the table. Some people like to do that just to make sure their working out doesn't get muddled, right? We know there is a gradient of 0 at minus 1, and now we've got to find the other gradients. Now, one of the things that's really important to note here is that I still put it in ascending order, right? They're reversed in the absolute value of their size, but remember, minus 2 sits further to the left on the number line than minus 1 does. So you need to put them in the order that they appear on the number line. And that's really important because remember, we read from left to right, and that'll establish whether it is a maximum turning point or a minimum turning point. If you were to put both of these into the calculator, you would get for the value of minus 2, you would actually get 9, and for the value of minus 0.5, you would actually get minus 9 over 4. Right, they're actually going to be the same values as this. That's just a coincidence for this function itself. So what we're going to have is we're going to get positive 0, so positive 0, negative. So we're going to get up 0, down, positive 0, negative, and that's going to mean this is a max TP. Okay, and that is how you do a table of values to test the nature of a turning point. So in every question that we're going to do later when we're sketching or doing maximum minimum problems, you always have to test using one of these methods, and it will depend on which method is better. For hard questions where it's really difficult to find the second derivative, using a table of values can actually be more efficient, even though it looks like it's a heap of work. It can be more efficient in some circumstances. But for a lot of curve sketching, all you need to do is find the second derivative which was up further. Yeah, so find the second derivative, and that can establish whether it's a maximum or minimum turning point. I just want to discuss one more thing about the values that I chose. You may note that it's a little bit odd that I chose a value of minus 2, minus 1, and then minus 0.5. Okay, why didn't I choose the value of 0 instead? Okay, I actually had a little bit of liberty in this, is I knew there would be a problem if I chose 0 when we were talking about our, when we were doing the second derivative, right? When we're doing that second derivative proof, because what we're going to talk about later is that center point is actually going to be a point of inflection, which will be when the second derivative is equal to 0. So that wouldn't have been able to tell us if it was positive or negative or not, if we were testing around there for the second derivative. I also just want to say, just make sure with your points that you make sure you try to stick as close as possible to the center point. If I'd chosen another point to test and I'd chosen 3, for example, I just randomly chosen 3. If we have a look at our function here, the value at 3 is going to be a positive gradient. So what I would have actually got in the end is I would have got positive 0 and then positive, and that wouldn't have given us a turning point. That would have been something wacky, right? That would have been a horizontal point of inflection, which we will also look at later. But that's not the case. What we should have got is going to be a maximum turning point. So it's really important that you make sure you don't test too far outwards away from where your turning point is. Otherwise, you may get anomalies where you go past another turning point. So just be aware of that. Try to test as close in as possible to your actual value. You can actually do a thing as well where into your calculator you could have done minus 1.1 and then minus 0.9. Those are both perfectly fine things, and you just input them into the calculator. It's perfectly fine to do that, and then you write your answer as a decimal. Right, so that's just some notes on how to do testing critical points using the 2 different methods. And we're just going to have a go practicing this on an actual question. So find the coordinates of the stationary points on the graph y equals e to the x minus ex and determine its nature. Note there is a difference between e to the x and ex. One is to the exponent and one is a product, so multiplied by each other. We are deriving And note that these are both individual terms, so we won't need to use a product rule for them. And E is a constant in this situation, so we do not need to worry about using the product rule on that component there. Right, so if we have our function y is equal to e to the x, e to the x minus ex, right? We derive it once to find our stationary points. Y dash is equal to e to the x minus e. Why does it go to just normal e? Because when the x disappears, that's all we're left with, right? We're left with just the constant attached to it because it was a power of 1. When we decrease that by 1, we're going to get x to the 0, which is 1. When we're solving for this equals 0, because we're finding stationary points, e to the x is equal to e. We know that e has an implicit power of 1. That's just what's attached to it, invisible all the time. So if we match these two together, we can clearly see x must equal 1. X has to equal 1. To find the actual point where that sits on the curve, what we do is we substitute that back into the original function value. I'll actually do this notation. F of 1, so subbing in 1 into the x value, is equal to e to the 1 minus e times by 1 is equal to e minus e. So it actually sits on the point 0. So it's the coordinate 1, 0. And now we need to test its nature. So either a maximum or a minimum turning point. It's interesting for this, I would never actually do a table of values for this because it's way easier just to do second derivative, right? Second derivative from this point here, y double dash is just e to the x. And we know e to the x is greater than 0 for all values. It doesn't matter what number we put into there, even though it's 1 and it's going to give us the value e to the 1, which is equal to e, it's greater than 0. Any value that we put into there is automatically going to be greater than 0. So what did I say with greater than 0? Smiley face, we're happy. So that means it's going to be a minimum turning point, right? So we can just write that there. 1, 0, that's our point, and it is a minimum turning point. Okay, thank you for joining me for this lesson. We went through just some stuff on how to test our critical points in the 2 different manners, and also an example of how to graph, how to find the coordinates in an exam style question.